So here we're going to go through the basic eViews tutorial. I assume you have all the question sheets in front of you. So what we've got to do first is got to import data into the into eViews. So here we go. New work file. The first one is going to be the time series data. That's got 182 observations. I'll anyway use the unstructured data. You could use dated ones, but it doesn't add a lot here. So here's our new work file. Let's immediately save that. Here we go as intro one. Now we need to import the series, import from file. Of course, you need to know where your file is. Goes without saying, it's here. Indeed, two sheets on that file. For the first part of the question, we use the term structure sheet. That looks quite all right, the data here. And we just import the data as they are. They have the right names, we can use them, that's all fine. There's a blank series here. We can delete, well, we can look at it and we'll see, that's the dates. Okay, I will leave it here. Perhaps I'll just rename it to dates, just in case you want to get back to that information. So, first one is create an informative and graphical representation of the data. So we could look at each series individually. We'll double click on them and go to view and graph. These are time series data, so we know that line graphs are the right ones. You can see here on the left hand side there's all sorts of things we can change about the graph, how it looks, the color of the border, what legend we have. We'll leave all of this alone. I'll leave that for you to experiment with. So we click on graph on OK, and we can see our file. So this is a 1 month yield for government treasury bond in the US. If we look at the dates, we can see at the time that's from 2001 to 2005. Interest rates here were between 1 and 3.5%, 3.5% only at the beginning of the series. You can actually quite easily now change, for instance, you could look at the differences. Okay, how much do the yields change? At the beginning, quite a bit, but then they're quite stable. The changes are around 0. You could look at the log differences if you wanted to, but let's look at the raw data. So that's looking at one graph in isolation. Let's close that. What about looking at all of the series together? So we could just highlight all of them and then open as group. Again, we go to view to see the graphical options we have, and we'll still use line plot. You can see there's actually quite a few more changes now, and that's because we've highlighted more than one series, so there are options about displaying them together. But we'll look at all of them in a time series, and yeah, that's what you can see. Let's just look at the graph all together. We'll see the legend here. We can see that the top one, the highest one, that's the 10-year yield. And the lowest ones, that's the one with the short maturity, the 1 month and the 3 month one. So throughout this period, we have what's called an increasing yield curve. The longer yields are larger than the shorter maturity yields. That's the most typical situation. So let's make that small again. We'll click that away. Well, we've done the first part of our job. We created a graphical representation. Next question, is there a significant autocorrelation? I can just quickly look at the question. Is there significant autocorrelation in the data series? So we'll still have all our 5 highlighted, so we can still open them as a group. We go to view and we can look at a correlogram. Now, if you want autocorrelations, you need to know that what you want is a correlogram in level. That means we want the correlogram for the data, not for the changes. And we can see for the first series, so that's correlogram of M1, we can now see a little graphical representation of the autocorrelation, and here are the numbers. So what you can see here are the lags. So the first row here is for first order autocorrelation. This is not the place to explain autocorrelation. You have to do this in your course. It's very high, 0.945, and you can see that here the line is 1. We can see this autocorrelation only decays fairly slowly. Even after 30 weeks, there's still 0.25 measure of autocorrelation, so clearly larger than 0. If you go a little further down, we we only get the correlogram for M1. So if you delete this group, if you want it for M3, you open M3, you go to the correlogram, and you get exactly the same information. And you can see that this is quite highly autocorrelated as well. You can see the same with, let's look at the longest maturity one, correlogram. Okay, and we see basically the same picture. Very high correlation for first order autocorrelation of 0.96, and it decays fairly slowly. So let's see, next talk. Are the interest rates with different maturities correlated? Okay. So let's highlight all of them again. And what we want here is correlation between the series. One way to look at that is the covariance analysis. And we tick on correlation here. We don't want the covariance. We just click OK, and what you get is a correlation matrix. So you have all the series in the first row and the first column. So what we see here is that value of 1, that's the correlation between M1 and M1, that's not surprising. Correlation between M1 and M3 is 0.987 approximately. Of course, the correlation between M3 and M1 is exactly the same. So it's a symmetric matrix. So as you see, you can see actually the correlation here of M1 with M3 was 0.98, between M1 and Y1 is 0.88, M1 and Y3 is 0.68, and so forth. Now I ordered these in increasing maturity, so you can see that actually the correlation decreases as the difference in maturity increases. That's quite typical for these type of interest rate data. But even the yield for 1 month maturity bond and a 10-year maturity bond, there's still a quite high correlation, about 0.5. So that was the correlation between the series. Let's close that. Unfortunately, deleted the tutorial file here. Next one, create time series of the year 1 year yield minus 1 month yield and 10-year maturity minus 1 year maturity interest rates. So 1 year minus 1 month and 10-year minus 1 year. So you've learned that we use the easiest I like is to use the command window. So what we have is difference. We say series. I want to create a new series. Now you have to give it a name, and I call it dy10 y1. That's the difference between y10 and y1, and then I just say how I want to define it. y10 minus y1, and then I just press enter. And here's my new series, dy10 dy1. You can of course see that this value is basically always positive as we have increasing yield curves. We saw that before. The yields for the longer maturity ones are larger than the shorter maturity ones, so this difference is positive. Now I want the difference between 1 year and 1 month. One advantage for having this in the command window is I can now just go in there and make the changes. I want year 1 minus M1 and make the changes and press enter, and it creates this new series here, dy1m1. So now we can actually see that in most cases they are positive, but there are some cases where they are negative. Let's actually just look at the graph of this one. So you can see the 0 lines here. Mostly they are positive, but on a few occasions they are just slightly negative. That means we have sometimes at the short maturity cases we have a flat curve, but for longer maturities it's still upward sloping. All right. So now, are these two autocorrelated? Okay, are the differences autocorrelated? So let's again look at one of them. We'll go to View, Correlogram, Level, and we can see that these differences year 1 to M1, they're still quite highly correlated. And they're possibly not quite as highly correlated as the levels. If you go to 30-week difference, we're down to about 0.04 correlation. That's much lower than what we had in the actual levels, but there's still quite high correlation. What about the other one? 10 year minus 1 year. Basically the same picture. All right, next task. Calculate the first difference for all 5 interest rate series. And then we want to know, are they autocorrelated? So firstly, we want a new series. The first difference, for instance, for the 1 month series, that means what we want is the value in each period of the 1 month field minus the value in the previous period. And the way how we do that is M1 and in parentheses -1, indicating 1 period lag. So where we dm1, here we go. This is our difference. Let's have a quick look at this. Now here you can see that's basically around 0 on average, and it's just sometimes positive, sometimes negative. And we want that for all the other series. So I'll just go back here. Now for the 3 month series, I just need to change this. Then for the 1 year, for the what's the next one, 3 years, and for the 10 years. Here we go. Yeah, all our new series are all starting with D. And now the question was, are they still autocorrelated? So let's look at the differences in the 1 month field. Correlogram. Actually, the correlation has largely disappeared. There's still significant correlation in the first period for 1 period lag, but after that, you can see they're very close to 0. Let's see whether that's replicated for the other maturities. Yes, basically the same picture. Quite significant autocorrelation in the first lag, so for 1 week lag, but it more or less disappears for the others. Let's check one more, dy10. Same picture. Okay. So estimate a regression with dm1 as the dependent variable and all other changes as explanatory variables. So dm1 and all others as explanatory, so I'll highlight all of them, then open an open as equation. Okay, so that's one way we could go about this, and I just click OK, and here's our regression. And let's see again, interpret the regression result. obtained. So here we go. What we can see is that overall quite a lot of the variation in the 1 month field is explained by the yield in the other maturities. Remember, that doesn't necessarily mean that we chose the M1 as the dependent variable, but we didn't really put a lot of thought into it here, basically no thought, so you have to be careful with the interpretation here. We can see the different slope coefficients, and it's quite clear that the ones that are significant are the 3 month field and the 1 month field ones. Okay, the later ones seem to be insignificant. They have very high p-values. For the 3 month field and 1 month field, you have very low p-values, clearly below 1%. So it seems that the changes at the shorter end of the yield curve are correlated with each other, but not so much the changes between the short end or 1 month end and the 3 and 10 year end. Anything else we want to see here? Number of observations. We had 181 observations. That's the standard error of the residuals, sum squared residuals here. F-stat, that tests the null hypothesis that all these slope coefficients are equal to 0, and here we have the p-value to that test, clearly 0, so we reject that null hypothesis. The information criteria here, Durbin-Watson test, that gives you a first indication of first order autocorrelation in the regression residuals. It's fairly close to 2, so there's possibly not a lot first order autocorrelation. So that's all I want to say here. Interpret the regression tester, you can restrict the sum of all coefficients without the constant to be equal to 1. So that's something we haven't really looked at yet, but let's see where we can intuitively do this. Most of the interesting stuff in regression analysis under the view button, and we are now interested with something relating to the coefficients. The confidence intervals, and what we have here is coefficient restrictions. That's quite interesting. Now we are asked to put restrictions in here. So what's important to learn here, let me just cancel this. I just want to move this next to the work file. So we have the work file here. You know from the introductory models that in here, in this little object, we have all the regression coefficients saved. So if I open this here, you can actually see exactly these coefficients in our coefficient vector here, in our coefficient vector C. I will always save the coefficients of the last regression. Okay, so you can see that here, and it's called C. So if we now go into coefficient diagnostics, wall test coefficient restrictions, don't worry about the wall test, it's test on coefficient restrictions. Technical details again are left for the course. I was asking whether the sum of these first 4 coefficients is equal to 1. And we have to enter this restriction, and well, let's do it. First coefficient plus second coefficient plus third coefficient plus fourth coefficient, is that equal to 1? So it's quite intuitive. You just click OK, and what we get is a test here. Actually, a number of different ways of how you can test it. Again, do not worry about the technical details here at this stage. We get certain test statistics, different test statistics. Let's just look at the p-values. Our null hypothesis is that this restriction holds. The sum of all coefficients is equal to 1. The p-value is in the region of 3%. So at a 5% significance level, with an alpha of 5 or 95% significance level, we would indeed reject that null hypothesis. If our alpha was 1%, we would not. So it's a bit of a marginal decision. But again, we didn't put too much thought into the actual regression, so we're not going to discuss this in detail. So next task. TestFlow re-estimate this regression only for the post-September 11 sample. Now, so that means we have, so that what that means is in September 11 in 2001, we have 3rd of August, our first observation. So we want to see which observation is actually after September 11. So good thing, let me now not delete the estimation. I click on estimate again and I'll get back to the specification window, but I need to cancel this, so close the coefficient. So we need to look at the dates. Fortunately earlier I saved this. So September 11, so the 7th observation is the first post September 11 one. So what we want to do is we want to exclude observations 1 to 6, or in other words, we want to use observations 7 to 182. So the easiest way to do that is to go in your command window again, and I'll show you how to determine the sample or change the sample. SMPL is the sample command, and you say we want from 7 to 182. Okay, and now you can see here in the work file there's the sample information here. Basically it says, okay, sample 7 to 182. If we now estimate, go back to the regression estimation. Let me just close that window out because I want to show you how to do a regression in a different way. So basically now, whatever we do, we use sample 7 to 182 only. So I told you, or we told you in the modules regression model, that one way to estimate a regression is to use the command line. You type in ls for least squares, and then all the variables. The first one is the dependent, dm3, dy1, dy3, and dy10, and enter. And now you can see, now we see the regression window again, and you see it has only used sample 7 to 182 because that's what we determined here. And of course, what I did forget, I forgot a constant. So let me go back to estimate and let me include a c for the constant. Here we go. And now we have estimated our regression equation just for a different sample. You can also easily change the sample if you just go back here to estimate, to our specification window. You can actually change the sample immediately here as well. I'll do cancel. So this is our different regression as a result. Again, I'm not going to talk a lot about the difference in the interpretation. So that was the first part of the tutorial exercise.